Okay, so today we start with lecture 1.8. We have been talking about transfer function representation of electrical, mechanical, and electromechanical systems. Today we are going to talk about rotational systems. So last time we did translational mechanical systems in detail. The treatment of rotational mechanical systems is analogous, very similar to the treatment of translational mechanical systems, except for one major thing, that is the presence of gears in rotational mechanical systems. So we're going to talk about this a little bit in detail today, especially because it is very relevant to electromechanical systems that we're going to do in detail later on in this unit. So the first thing would be to see what are the basic building blocks of rotational mechanical systems, and it is very similar to what we have seen in translational mechanical systems. There are uh, there are three basic building blocks, just like uh, electrical systems and translational mechanical systems. So there is this spring which is to a a rotational uh, force, which is torque actually. So you're trying to move this spring, give it an angular displacement, right? So the relationship would be similar to what is the relationship for the force displacement of a spring that is subjected to linear displacement. So if you subject this spring to an angular displacement using a torque T, the force angular displacement relationship is T is equal to K theta, right? Or if you want to write down the torque angular velocity relationship, then you'll write down torque is equal to K integral of angular velocity, right? Omega tau d tau 0 to T. Again, like the translational mechanical systems, if you want to find the what we define as impedance of this particular element in the rotational system, the impedance is going to be the torque divided by the angular displacement. So Ts divided by theta s in the s domain. So if you find that out by taking the Laplace transform of this equation, you'll get K. So this is again similar to what we found in translational mechanical systems. The impedance of the spring was K. In a similar way, you have this viscous damper, which is denoted by D, a simpler relationship. Dt is equal to d omega t, right? So the torque that has to overcome the viscous friction, the viscous friction is proportional to the angular velocity of the this piston that you're trying to rotate. So basically, it's similar to what you had in translational mechanical systems. And if you want to write down the torque angular displacement relationship, so it is going to be Tt is equal to d theta by dt. Again, very similar to what we have seen before. And the impedance, which is t by theta, ts by theta s, would be ts if you take the Laplace transform of this equation. Similarly, the third important element of rotational mechanical systems is the inertia, right? Inertia J, and the inertia is basically replaces mass uh, from translational mechanical systems, right? So in rotational mechanical systems, we have inertia towards the motion, inertia towards rotation. So if you apply a torque T and the resulting angular displacement is theta, then the relationship is equal to basically Tt is equal to J times angular acceleration, right? Which is equivalent of force is equal to mass into acceleration. So torque is equal to moment of inertia into acceleration, and this acceleration is angular acceleration. So you can also write it as Tt is equal to J times d omega t by dt if you want to write down the force, a torque angular velocity relationship. So if you take the Laplace transform of this equation, you will get T of s is equal to J s square theta s. And if you want to write down theta s by ts for this, you'll get Js square. Sorry, if you want to write down Ts by theta s for this, you'll get Js square. So that's what you get here. And so you have these three basic impedances in the S domain for rotational systems. Now let us take an example and see how this is done actually in practice. Coming back to the notes. So suppose you have a physical system which is a beam which is being subjected to a torque at one end, right? So a torque at one end, and it is undergoing some torsion. Torsion is some mechanical, say, displacement along the longitudinal axis, right? So equivalently, it is represented in this case. This is an example from the book. It is represented in this case by two moment of inertias, J1 and J2, with two dampers D1 and D2 coupled together by a spring. So this basically models this actual rotational system, right? Which is connected to bearings on both sides. So this is the physical system that you have, which is being subjected to a torque and consequently undergoes some torsion, right? And this is the schematic for it, the equivalent diagram for it in terms of the three basic building blocks that you have, right? And now we are supposed to find the transfer function for it. Right? So the basic process is similar. The process is very similar to what we have done in translational systems. The first thing that you have to do is to identify the degrees of freedom, right? So how many linearly independent motions are possible? So if you fix every possible motion and you allow one motion to happen, how many such motions can happen? So in this case, suppose it seems to be that there are two possible motions. One is because of J1 and the other is because is the angular displacement of J2. So if you fix J2, can you still move J1? Can you still rotate J1? Yes, you can. So theta 1t is possible even if there is no theta 2t, if theta 2t is made 0. Similarly, if you fix theta 1t, if you fix this and this inertia here, can you still rotate the other one? The answer is yes, you can still rotate J2 because even if you fix this, you can still rotate this, and this will undergo some angular displacement, right? So there are two degrees of freedom in this. And how do we basically write down? So we can write down by the inspection method, but let us do it by first drawing the free body diagram for this. So how do we draw free body diagram for rotational systems? We take this J1, right? Let me draw it slightly below. We take this J1, right? The J1 moment of inertia, and we take this J2 moment of inertia, and let us see what are the forces. So the first case would be when theta t is not equal to 0 and theta 2t is equal to 0. So you are allowing one of the two motions. You're allowing this to move, you're allowing this to move, and you are not allowing this to move. So in that case, what are the forces? So now let us see what are the forces. We have to the torques. The torques we have to draw in the counterclockwise or the clockwise direction. So looking from the figure, you can see that this torque Tt is in the clockwise direction, right? So we draw this T of t in the clockwise direction here. So this is T of S, right? In the clockwise direction. We draw this in the S domain. And this theta 1S also takes place in the clockwise direction. So we're drawing this reference direction for angular displacement theta 1S. Now what are the forces that will oppose this motion, right? So what are the forces that will oppose this force, this torque Ts? So when this theta 1S displacement takes place, it is going to be opposed by the damper, right? So you have S d1 theta 1s. It is going to be opposed by the spring, so you have K theta 1s. It is going to be opposed by the inertia J1 in the opposite direction, right? So it is going to be J1 S square theta 1s. So these are three opposing forces that are going to act. These are three opposing torques that are going to act on this. Is there anything else now? No. So what about J2? What are the torques on J2? So we are talking about the first case, right? So J2 is not undergoing any angular displacement. We have fixed J2, right? In this case, what is going to happen is that only the spring in between, this spring that is in between, is going to transmit a torque to J2 because this spring is being compressed, right, in the clockwise direction. So it is going to exert a counterclockwise force. It is going to try to uncompress itself in the opposite direction on J2. So that is the force that is going to be transmitted to J2. So uh, so you can understand it like this. So this is your spring, right? And you are exerting a torque on this like this. You're trying to compress it like this. So what you're going to wind it up like this. So when you're winding up it up like this, it will try to unwind itself. So to in order to unwind itself, it is going to right. It is going to exert a force, a torque like this in this direction, in the counterclockwise direction, and in the clockwise direction on this side, right? So these two directions would be different, just like in the case of the spring, right? When the spring was compressed, you compress the spring like this, it tried to force, it tried to uncompress itself by by exerting a force like this in this direction and exerting a force like this in this direction. So you can also imagine what is if you're holding your hand, if this side you're holding this spring with your hand, and somebody is trying to is trying to apply a torque in the clockwise direction, with this spring in his hand, in the other hand. So what is the force that you'll feel a force in the clockwise direction, right? So the force on the spring here is going to be in the clockwise direction, opposite to the torque that was here. So it is going to be K theta 1s. This is the only torque that is going to act on J2. Now, what are the torque? What is going to happen in the second case? In the second case, you have theta 1t is equal to 0 and theta 2t is not equal to 0. So this is your second case, when you have the first displacement 0 and the second displacement is not equal to 0. So in that case, what is J1? What is J2? What are the torques in J1 and what are the torques in J2? So let us talk about J2 first, right? So if your J2 is undergoing a, and what is the reference direction for theta 2, right? That is also important. So theta 2 is, again, you're assuming that this is the direction in which this displacement theta 2t takes place. So now let us look at this diagram and see if this moves counterclockwise. What are the forces that are going to, what are the torques that are going to act in the opposite direction? So again, the spring, the damper, and the inertia are connected to J2. So you can make the three torques. So the spring, which is again K theta 2s, right? The damper here, which is S d2s, right? S d2 theta 2s, and the inertia, right, of J2. So S car J2 theta 2s. So these are the three torques that are going to act on J2. And what is going to act on J1 is again what is common between the two, what is linking the two. So this K theta 2s, which is counterclockwise here, right, is going to act in the clockwise direction here. K theta 2s. So now let us sum the forces, the torques together. So what are the total, what are all the torques that are acting on J1 when both the cases are taken together? So when both the cases are taken together, then the sum of the torques is going to be this, right? So these are all the torques that are acting. And when the two cases are taken together, what are the torques that are acting on J2? So these are all the torques that are acting on J2. So what you can do is you can sum the torques that are acting in the clockwise direction and equate them to the torques that are acting in the counterclockwise direction. So if you look at the first figure, we can write down Ts plus K theta to s, right, is equal to this is equal to j1 s square theta 1s plus k theta 1s plus s d1 theta 1s, right? And what about the second? So basically, you'll actually combine these two free body diagrams and make one. But because of the shortage of time, I'm not doing it. I'm just writing it directly from the two separately. So what about the second diagram? So you have in the clockwise direction, you have k theta 1s, right, is equal to, and in the counterclockwise direction, you have k theta 2s plus s d2 theta 2s plus s square j2 theta 2s. So these are the two equations that you get, and let us now write down these two equations together. So what do we get in this? If you try to put them together, the first equation, so it is j1 s square plus k plus s d1 theta 1s minus k theta 2s is equal to ts, right? This is the first equation, and the second equation, uh, k sorry, let us write it like this: minus k theta 1s plus, so I'm taking this to the right hand side, plus s square j2 plus s d2 plus k theta 2s is equal to 0. Now if you write this down in matrix form, what is that you'll get? You'll get j1 s square plus sd1 plus k, j2 s square plus sd2 plus k, minus k theta 1s theta 2s is equal to ts and 0. So if you look at this matrix equation that you've got, you will very easily see that this is something that you could have got by inspection also. So if you try to if you see the diagram, if you see the diagram, you can see that all the impedances that are connected to theta 1 are j1 s square, k, and d1s, and all the impedances connected to the angular displacement theta 2 are j2 s square, d2s, and k, and what is common between the two is k, right? And that's what you have got here, right? And now you can very easily find out whatever transfer function you want to find out. Suppose you want to find out theta 2s by ts, you can find that out by finding theta 2s using Kramer's rule from this. So theta 2s is going to be the determinant j1 s square plus sd1 plus k minus k. Replace the second column by this ts0, this determinant, divided by this determinant, the actual determinant delta of 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 this matrix here. So you can find out theta 2s from this equation, and correspondingly you will get theta 2s by ts, which is the transfer function that you're trying to obtain. So I hope this is clear. So we can write down the equations by drawing the free body diagram, and we can write down the equations by the method of inspection. In the next lecture, we are going to talk about what is going to happen if there are gears in the rotational mechanical system. Thank you very much for listening.